Hello and welcome to our PowerPoint presentation on the redesign of the folding cup holder that's in the Cirrus Model SR20 aircraft. Presenters will include Michael Herron, Jacob Kale, Blake Spurgeon, and me, Bailey McDaniel.
Currently, I work at Sweet Aviation in Fort Wayne, Indiana as an aircraft mechanic where we are a Cirrus service center dealing with all things related to Cirrus aircraft. On a monthly basis, we will get a write-up from an instructor or an aircraft owner stating that the cup holder is broken. After noticing this happening quite often, I paid attention to each cup holder that was replaced. I started to see a pattern with a missing linkage that is shown below with the red arrow pointing to it. Our group determined that the failure is occurring because of the folding mechanism is spring-loaded. The cup holder can be forcefully opened, causing fatigue cracks on the lower pin. After being opened many times, the stress builds up in the lower pin, causing it to break off or come out of place. This results in a missing linkage and causes the cup holder to malfunction when being closed. The purpose of this project is to develop a more simple design and a cheaper product. Our goal was to increase the strength of all parts while maintaining the original cup holder's size. Anything that permanently goes on an aircraft can be considered critical weight. We measured the original cup holder at 141.7 grams and the 3D printed cup holder at 105.9 grams. We were able to reduce the weight by 25.3%. Our group decided to maintain the folding mechanism. The folding mechanism was designed for the ring to fold within the outer shell using 4 total linkages. A set of 2 linkages would hold the ring at 90 degrees, while the other set would rotate the ring in or out of the shell without interference. To eliminate existing mechanical failures, we removed the spring-loaded ring, making it so the part would not slam open and eliminates unnecessary stress on pins that allow the cup holder to open or close. For our initial performance specifications, we wanted the cup holder to safely hold a 30-ounce stainless steel cup and for it to accommodate smaller sizes as well. The ability for the cup holder to open and close in one motion was also important. We had planned on using an LED light that was activated when the cup holder was opened. The LED light would have been red and mostly used for pilots flying during night hours. This LED light would have used a watch battery and a micro pressure switch that would allow it to be turned on when the cup holder is opened. We also wanted to maintain the same dimensions as the original cup holder.
So to calculate the stresses in various components of the cup holder to ensure they were strong enough under the load that we designed it around, we used the drop force tester in the physics lab. And so from here, we hung an equivalent mass from that bottom of the tester and dropped it from 3 inches. So we chose 3 inches because that was the height from the base of the ring to the base of the cup holder. So we figured if it was above that ring, it probably wasn't going to go back in to the cup holder itself. So like I said, 3 inches was our worst case scenario. So we did 20 drops and we got the average of 177 newtons, as you can see there on the right side of the screen in that table. So this dynamic force simulates if the plane suddenly lost altitude, had a hard landing, or even if the cup was not on the base when released from the hand. So then we used this average force into calculations of finding stress elements of the cup holder. So ensuring our design was strong enough, we used various free body diagrams to find the stress in the 90-degree support linkages and the linkage pins. These areas, or these components, were the biggest concern for us just because they had the smallest area. So as you can see on the right side, we used that average force that we had earlier from the previous slide, and we converted that into English units, so pounds. And from there, we calculated the force of the 90-degree support. So this linkage is going to hold that base and the top piece at 90 degrees. So we used a beam style of free body diagram, and we used the moments and found our support, or our force, in the 90-degree support. And there we got 45.48 pounds. All right, so in calculating the force in the linkages that we're holding it at 90, we used the sum of forces y with that free body diagram there on the left side, and we found the force in both linkages were 61.74. And so since we had 2 linkages that were holding it, we could divide that by 2, and we got 30.7 pounds of force in each linkage. So from there, we knew the highest stress was going to be in the slotted portion of that linkage. So we calculated the area of that section, and then we used stress equals force over area, and we got 2,190 pounds per square inch roughly. So we then compared it to the PLA tensile properties. So we're using in the ASTM D638. So in that value was 9,000 psi for its yield strength. So from there we can see that we are well under that yield strength for that PLA. So after finding the stress in the 90-degree linkages, we wanted to find the stress in the pins that were holding those together. So we used two free body diagrams for that. The first one, we just split the force and the linkage into X and Y components. And from there, we used the next one to find the total force on the pin. So after all the calculations, their pin total force was 30.89 pounds. So next we calculated the area of the circular pin and then found the shear stress using tau equals force over area, and we got 1,214 psi roughly. So we compared it to the yield strength, but likely it'll be a lot lower because it's in tension. So we were well over that with a factor of safety of 7, so we would assume the device was safe, and we were going to verify that after testing.
And here it is, the redesigned cup holder. You can see on the left image it being completely open, the middle image being slightly folded up, and the far right image being mounted and fully closed and out of the way. You can clearly see the pins and how they are in their linkages and how they travel in their linkages in the middle image as the cup holder is folded back up. And closing the lid also pulls the ring down and inward, so it's kind of a one motion process. This design is a whole lot simpler than the existing cup holder and still maintains the folding function of the cup holder itself.
After the design and calculations were complete, the group developed a plan to test prototypes of the cup holder. The first test we performed was on the 3D printed components. Fortunately, a couple members of the group had experience with 3D printers and know how they would function and what issues we would run into. 3D printing is a cheap and relatively fast method for prototyping, but also comes with flaws. The filament can shrink as it cools, creating a part that is smaller than design. As a result, we printed the design and measured the shrinkage and made adjustments to the design to accommodate. We then assembled the design and verified that it functioned properly, and it did. Lastly, the current COVID-19 pandemic prevented the group from testing the cup holders further, but there was a plan to test our calculations and strength of the cup holder by applying dynamic loads to the cup holder to verify the original problem was fixed. Throughout the project, the group experienced several problems. Most of the issues were minor and didn't affect the scheduled completion of the project, but there were 3 issues that caused delays. The first and largest issue that the group faced was the design itself and getting the ring that holds the cup to close quickly enough that it was out of the way when the bottom of the cup holder was fully closed. This issue took several additional hours of SOLIDWORKS design and physical trigonometry calculations to fix. As stated in the previous slide, 3D printing tolerances also caused issues that were expected by the group, but still slowed us down because a couple prints were required to ensure the fits were correct. The COVID-19 pandemic also prevented us from accessing the school's 3D printers or even meeting face-to-face to perform additional testing. As expected, the specifications of the components had to be changed as the project progressed because of the 3D printing shrinkage. The initial design was around slip fits of 1,000ths to 5,000ths of an inch. The shrinkage of the 3D printing PLA required the group to increase these clearances greatly, and in some cases as high as 25 thousandths of an inch. If the group is able to go to production with the cup holder, injection molding would be the preferred method because the tolerances are much tighter and the finished results are much more reliable.
This slide breaks down the cost of 3D printing one of the cup holders and why injection molding not only would yield a better part, but also at a cheaper price per assembly. At 8 cents per meter of a filament, the PLA used in the 3D printing process ended up requiring around 41 meters of PLA to complete all of the parts. Assuming a cost of around $2 per hour to use the printer and factoring in the 9.5 hours of print time, the total cost in terms of time to print one cup holder resulted in around $19.24. The total filament ended up costing around $3.28 to complete, which, if all totaled up, a 3D printed cup holder would cost around $22.52. We guess that if one were to use injection molding for this process, the price per cup holder would dramatically decrease to a value of around $5 per cup holder versus the $22.52 for the 3D printed cup holder. The 3D printing process is great, but only in terms of printing one-off prototypes. Large scale, the injection molding process would end up yielding better quality parts at almost a fraction of the price. Since the coronavirus has affected the whole globe, it's also affected all of our schooling and the projects that we were planning on doing for school, and our project is no exception. So since the virus had hit the planet, some of the additions that we were planning on doing to the cup holder changed. We didn't end up getting to add in some design implementations that would have made the cup holder even more than it already is. The first one being a retaining strap. So if you're looking from the front of the cup holder, on the left side of the ring to the right side of the ring, what we would have done is attach some sort of retaining strap that would have connected between the 2 points. It would have been easily replaceable and would probably have been made out of some sort of elastic fabric. This would have allowed the cups to basically not fall out of the cup holder, so it would prevent smaller cups that maybe weren't necessarily the full size of the ring from falling out of the gap. This would include things like smaller water bottles, or even smaller cups that aren't the 30-ounce stainless steel tumbler that we designed around. The second would be a tension flap, so right in the middle of the ring on the upper part of the cup holder, we're going to attach some sort of tensioner flap that would be spring-loaded and would press into the cup. It would actually press the cup into the retaining strap. It would just add some necessary tension to the cup to prevent it from rattling around. This would basically just keep the cup from moving around within the ring itself and would add to the secureness of your beverage. And the third, like Blake said, would be the LED light. We would have done some sort of recessing in the design to allow for the wiring to be flush with the top of the cup holder, so it wouldn't protrude out, and we would have, like Blake said, used some sort of watch battery and a micropressor switch to allow the light to be activated upon opening and then deactivated upon closing. And the light would have probably been red simply because the rest of the lights in the interior of the plane are red. And this would have been a really nice feature to have on, say, a night flight. The redesign of the Cirrus SR20 aircraft's folding cup holder was, in our opinion, a success. The redesign was lighter weight with a 25.3% weight reduction. It also has a simpler design, minimizing the amount of moving, mechanical, and spring-loaded parts in the assembly. The simplicity minimized the amount of failure points and ensured the longevity of the new cup holder as well. This redesign, although initially designed for the Cirrus SR20 aircraft specifically, makes for a great folding cup holder for just about any vehicle. The current 3D printing process proves to be difficult with tolerance issues. Although it's great for a one-off type prototype assembly, any future or mass-produced options for this redesign should probably be done with injection molding, as it would be cheaper and would produce better quality parts in the end. Thank you for listening to our presentation, and although we had hoped we would have done this in person, we're thankful to at least have the opportunity to present something. Thanks.